All right, so today we have Jay Dawani, CEO and founder of Lemurian Labs. Um, they are building some interesting things that we'll dig into in the context of broader trends in AI and machine learning. So, Jay, welcome to the Data Exchange podcast.
Thank you for having me, Ben.
So, I guess the first question for you is what's the overarching megatrend that prompted you to start a company?
Spent about a decade working in AI at the frontiers of it and started working on some of the early foundation models back in 2018, focusing on general purpose autonomy back then. And, it was a 2 billion parameter network back in January 2018. And I was already exhausting clusters like 512 GPUs. And I started looking at the trajectory for where I needed to go. And I'm like, no, these models need to grow like 100 to 1,000x bigger. Right? And I was looking at them like if you model out the compute, right? And you're never going to saturate compute perfectly, so you can't just model out linearly. So I started looking at that. I'm like, yeah, I basically need 400,000 GPUs. So where do I go and get 400,000 GPUs? And that became one of the big questions for me. So went and spoke with a lot of the semi companies and the hyperscalers to kind of get a sense of whether or not they would give it to me. Some of the companies felt open to it, some were aligned. I was considering joining some of the self-driving companies at this time or one of the semi companies like NVIDIA. And it kind of felt like there was a massive disconnect between what was happening on the semi side, what was happening in software, and how the AI companies were thinking. And it felt like we were further and further off at this point from actually realizing the promise of a lot of these models. So once I kind of saw that, I'm like, why do we actually need that much compute? Like, what's actually wrong here? And there was a lot of things. The architecture itself, the software stacks we have, and they're super fragmented and brittle. And then you have the hardware, right? And that hardware was built under assumptions for a very different world than the software was, and then what these algorithms are trying to do, right? So you have these tectonic shifts happening in different places, and they're getting ripped apart in this way. So that was increasing overall cost and energy consumption and so on. And it felt like the thing that needed to get changed was computer architectures to be better suited for these AI workloads. And eventually did that, designed a chip, and realized that the bigger problem was software. And so now we've been focusing on that quite a bit.
So I guess uh, just kind of rewinding a little bit from at the start of what you just said there. So obviously the models are still getting bigger, right? So I guess listeners who are regular listeners to the podcast might be familiar to this phrase scaling laws. And I think that so scaling laws, roughly speaking, meaning if you increase the data in compute, your models become more capable, generally speaking, right? So, um, and actually, Jay, uh, the model since you started got bigger, so the scaling laws were followed. But now, even when you talk to the people in the teams who are building these foundation models, I think their working assumption is to get to AGI, they still have to go down, they still have to follow scaling laws, right? So the models kind of uh, need to get bigger unless there's some fundamental breakthrough. Right now, at least the working assumption is their models are going to get bigger. They'll need more compute. So is that, am I correct there?
Yeah,
I
so
mean, that's how they think, not how you think, but
absolutely. So the
yeah.
general view of the space is models do need to get bigger, right?
Mhm.
And there is a truism in that. Models will have to get bigger because more capacity in those models, more degrees of freedom. So you have a larger state space that you can search. And you're always trying to search for a certain program or certain neural circuit representations that you can build other things out of, right? And the more space you have to navigate and search through, the more you will find something that is useful, right? Or the better chances you have at least. And there's ultimately three things that matter when it comes to neural networks. You have an inductive bias, you have scaling, and you have priors, right? When you don't have compute or a lot of data, you really want to focus on inductive bias and prices or your biases, right? And it's basically enforcing your knowledge and opinion of the problem and how to solve it into the structure of these neural networks, so you don't need as much data. But if you're trying to go for generality and a whole lot of intelligence, you actually don't care as much about structure or putting these biases because you want the data to kind of do its own thing and you want it to fit to that best. So models will get bigger. And we keep finding this. Whenever models do get bigger, they have more capacity, they'll learn, you have some form of emergence. Um, and emergence, of course, as most listeners know, is capabilities that were unplanned for that came out, right? And they were just surprising. But that doesn't always work for every kind of thing. So sometimes you'll find some task got worse or some had no impact from scaling whatsoever. And there's a whole bunch of new things that we're constantly finding out, or some just saturate. Like you can't get better than that, regardless of how much computer data you throw. So there's a lot that's happening there, and it seems to hold true.
So you personally and Lemurian Labs, are you focused mainly on pre-training or inference or both?
Both,
Both.
right?
Okay.
We're going to have to do both, right? So right now, training is still the dominant cost, right?
Mhm.
And it will be for a while.
Although if you look at the financials of some of these foundation model companies, obviously they spend a lot on training, but the operation of the models, given that there's somewhat of a race to the bottom in terms of pricing, you can't really jack up your price because there's alternatives, right? So there's not a lot of differentiation among the model providers, right? So
Yes,
yeah,
there's some things you can do to differentiate, right? So
yeah.
there's your opinion on the model architecture, the data set you collect, how you do pre-training, like RLHF and its variants. There's other techniques like that. People going and trying to do chain of thought. Others are doing RAG. Others are really focusing on getting better pre-training done so you can actually create more capable base models because the capability of the base model itself really, really matters, right? And then you want to try and take off a lot of its constraints or add in the right boundaries in some cases. And that's what RLHF does. It surfaces new capabilities by giving it more structure.
But
And
as someone who uses multiple endpoints, right? So from Llama, Gemini, Claude, and OpenAI, uh, they all have their strengths and weaknesses, but it's not like one of them can really kind of start charging you a lot more money. It's not like, okay, now that this provider is charging me a lot of money, I'm going to pay them because the other models are so much worse. I don't think we're in that situation, right?
we're not yet. I mean, each of them has things that they're better at. I mean, you'll find this. It,
Right.
depending on how they've constructed their training data set and how they've done pre-training and everything else, certain capabilities will be better with certain companies, right? So you kind of want to route your tokens into multiple of them, and then there's companies working on that as well and trying to keep
And
services.
there, you obviously can also do your own fine tuning or RAG or something, right? So yeah.
Yeah. But if you think about the overall cost, right? So it's never just one model that's being trained in most of these companies, right? They have multiple different bets, each of those, and you're always thinking about what is the structure for that network that also can scale up, right? Because you don't want to just do things that make sense in the small. They also have to scale up because that is where the value is going to come from, or more capabilities are going to come from, right? And this has been proven in the bitter lesson from Sutton, learning and search are the two things that actually scale. Um, and this is very much true when it comes to neural networks. So training will be a thing, and then you have model collapse also being a thing, data drift, and so on and so forth. So you have to retrain those models quite a bit, and retraining is very expensive, especially today with the size of the clusters, the amount of data that's being ingested. But then, yes, inference is also a thing, especially if you're operating at massive scales, like some companies are starting to. But inference is something that we know how to make cheap.
Yeah.
And it's doable to actually take a large model and make it 1,000x cheaper. Like you can do knowledge distillation, you can, it's a whole bunch of tricks you can do when it comes to blocking, tiling, fusing, quantizing, sparsity, um, and how you,
The things that the computer vision folks have kind of learned over the years, right? So
yeah, I mean,
I-
well, everything from HPC is becoming relevant for ML, right? If you,
yeah.
the best way to think about modern day AI is high performance computing inside of a cloud environment, right? So every single trick that the HPC folk have been doing for the past few decades is now having to trickle into the ML world. So there is a bit of a knowledge barrier or skill barrier between the two worlds, and that does need to get combined, fused. And that's part of the role that we play. We're building new software stacks to make it easier for people to do those optimizations, or in some cases, not have to think about those optimizations, and our stack will take care of it for you to a large degree. Now, we can't do everything because there's a limitation to how much compilers and runtimes can do. So you have to relegate some to the engineers, and you can take care of some. And then hardware, of course, hardware is constantly getting better for these workloads and getting tuned for it and for the software stack. So there's a massive interplay, and inference will get cheaper over time. Right? I'm not overly concerned about the cost of inference. I am concerned about the cost of training and how big models are going to have to get to and what the limitation over there is.
So you described earlier on that you folks started your journey mainly focused on hardware, but now kind of your focus is on building a software stack, right? So
Yeah.
so when someone talks about software stack in this context, people think of CUDA, ROCm, Triton, right? So OpenAI, Triton. So tell us about what you folks are building.
Yeah, absolutely. So it might make sense to actually trace it through where we came from and how we got here. Right. So we started as a semi company, and we developed a number format called PAL because you really want efficient ALUs that have good representation and good numeric properties for a lot of these operations. And if you are squeezing down bits, you want to make sure you have enough representation in there to actually have networks work stably, right? Because when you do quantization, you actually perturb the network and change its behavior, right? And you can't actually figure out exactly where, but neural networks require a certain amount of precision in certain areas. So we designed a format for that. And then we designed an architecture around that, and it was a distributed data flow architecture. It was one of the first of its kind, and it was insanely powerful, right? But the problem with building a new silicon is the world, or at least your customers, and your customers are ML developers that really have jobs to do and they care about doing certain things, or at least have gotten accustomed to doing things in a certain way. So you have to fit that world and the way they think, right? Because a good product isn't something that is just super cool or something for developers or other engineers to talk about amongst themselves. It has to solve a real problem for somebody. And in our case, if you think about the ML world, developers are accustomed to sitting in PyTorch or TensorFlow or Caffe or Onyx and so on and so forth, and or JAX, and they want things to compile and they want things to run, right? And people are constantly coming up with new things. Right? If you think about PyTorch, there's over 2,000 operators in there, right? You need to have coverage of those operators and have them running on your hardware, especially if you're doing training. And in some cases, inference, they have unique insights into certain kernels and the way they want them to run, and you need to have support for that, right? But if things are entirely new and the world is changing really fast, it is very hard to build a stack that robust while you're building a chip and deploy it in a tight timeline. And most clouds want to see at least 2 to 3 generations of production silicon with working software before you can actually gain traction.
And
So
actually,
basically,
this is a good point because in the chip side, there's also the distribution problem, right? So
yeah,
how do you get people to actually use your chip? Well, for one route is to convince the cloud providers, but the cloud providers, well, Google
their
has
own.
Google has TPUs,
Yeah.
right? So and the other cloud providers may not be as motivated, right? So
They are. Every single hyperscaler and CSP I know, barring maybe one or two, has a silicon trajectory. They're all building their own. They have in-house teams
yeah,
that
no,
are
but I
working.
mean, in terms for a startup of putting some
Yeah.
startups chips on their data centers, right? So,
Yeah. I don't see that really happening today, and we're seeing that in the market. A lot of folks that had a lot of promise, that had good architectures, have been struggling because software was mostly an afterthought, right? So we wanted to flip that on its head. And the other reason we wanted to really focus on software is the world is moving into heterogeneity, right? That's not something you can run from, right? There's that saying, everything that happened in mobile will happen in the data center, right? So we're basically starting to see accelerators accelerate everything, because you have to. General purpose has its limitations, but general purpose will continue from larger integration of specialized parts, right?
so,
But that,
so stop there. So when you use the word heterogeneity, the image I have in my mind is I have a cluster where I'm going to train a model. Half my cluster is NVIDIA GPUs, a quarter is AMD GPUs. Maybe some of them are, some ASIC like Cerebrus. Is that what you mean by heterogeneity?
That is one way of thinking it, and I hope that's not the world we end up in, because that would be ugly. But it's more if you're thinking about a supercomputer, right, which is what we do all of our AI work in today. You have a CPU, you have a GPU, you have interconnects, you have PCI buses, you have different memory, right? Over architecture generations, you can have like your L3 cache can be something else, right? It doesn't have to be the normal way we do things. It could be like from the DRAM side, it could be HBM, it could be GDDR, it could be LPDDR, it could be something else, right? We went in a 2.5D integration world from a packaging point of view. We went to do multi-chip modules. We're kind of moving in towards chiplets right now. Then we're going to go 3D, right? And each of those completely changes how you write software and how data moves around. And the algorithms and everything have to change to adapt that so you can actually saturate compute. I mean, that's ideally what I want. And that means programming models will have to get disrupted. How developers write code gets disrupted. The execution model has to change, but now you're talking about multiple different programming models and execution models that have to tie to that hardware and get updated really fast because we're kind of going into not just heterogeneity, but also having large-scale co-design from the workload to the software stack to the hardware and the overall system. And they're moving at faster depreciation cycles. And if that's what we get into, the bottleneck is software.
So based on what you said there, so so right now, right? So in my mind, I'm thinking, all right, so I'm training a foundation model. I'm writing it down in PyTorch, and maybe I have a team in charge of distributed computing or maintaining the compute infrastructure. So what's going to change in this picture? I mean, based on
Yeah.
what you said. So
The world that I'm trying to move us into basically is I want developers to stay in PyTorch. I don't want them to have to think about all the open source libraries and other things that sit between Triton and CUDA and
Mhm.
ROCm and so forth, or MKL or 1DNN and
Yep.
something from any other company. I want to unify that space. It doesn't make sense to have to think about the massive number of libraries and dependency managements between all of them and how things constantly break every single time. And that's just for training. And the amount of mess you have to go through to actually package that model and serve it. And if you're serving it, right, today, there's a different cluster for training and a different one for inference, right? Because they're optimized for memory bandwidth. And so one's optimized for throughput, the other one's a little bit more focused on latency. So the way you would write code and optimize it are different for both of them. But getting performance out of these things is really hard. It's specialized knowledge. There's less than 2,000 people in the world that actually know how to do performance engineering, right? And 80% of them are concentrated on one provider. So you need to be able to actually break that down and be like, hey, if you want to go from one hardware to another hardware, or you want to train on one hardware and go to a different one, and if you're a cloud, you have your own silicon, you should make it easier for yourself to actually go in any of these places and go to the hardware that gives you the best system perf per TCO for that model.
All right. So let me play devil's advocate here. So obviously, NVIDIA has invested many, many man years or person years on CUDA.
Mhm.
I think AMD ROCm is getting better. I don't know. I mean, so I guess one way to think of it, maybe they're 80 to 90, maybe optimistically 95% there in terms of being as usable as CUDA. Uh,
I think,
OpenAI Triton is open source, so kind of a mixed bag, I believe there. So why should we believe you, Jay, that
yeah,
you can build something that will allow us to train our models on any hardware without thinking about it?
yeah, good question. So one is incentives, right? Not everyone has the exact same incentives. Now, most of the AI companies are GPU houses. They
Yeah.
kind of have. Now, they all buy GPUs from one company today.
Hmm.
And Triton was designed because it's really hard to write CUDA kernels and do it well and get performance, right? So you have a higher level Pythonic-like interface, so you can actually generate CUDA kernels and get performance out. And it's roughly the same performance, like not totally, but most of the time.
Yeah. So give us a quick update and a quick description of Triton and give us the state of Triton.
Ooh, state of Triton is constantly changing, and they've got a whole good.
No, in terms of your rough assessment of maturity and usability.
Yeah. See, like Triton's pretty well adopted. Like PyTorch is looking at it as Triton as a backend right now, and I think it's actually been released on PyTorch 2. It's being used by OpenAI. I believe Meta is using it as well. Because OpenAI is using it, Microsoft's using it as well. I think there's a couple of other AI houses that
I
have
think
started.
OpenAI hired some of the key Triton people, right?
Well, they developed Triton, so
Yeah.
it makes sense, right? So it came from H.D. Kung's lab at Harvard. I think
Yep.
it then ended up at OpenAI.
OpenAI. Yeah.
So there's adoption there, right?
Mm-hmm.
But it is too tied to one hardware platform to be useful for any of the others, right? But what you want is a Triton and a CUDA equivalent kind of thing for every other hardware that can
Right.
also scale.
Yeah. Right. And
Because,
that's what you're trying to do.
yeah,
And I guess going back to my devil's advocate question, so why should you, a small startup, be able to do Triton on every hardware?
yeah, well, it's hard for any of the CSPs or the semi companies to do it, right? They all have their own alliances, they have their own roadmaps, they have their own things.
Or they may have their own software stack like AMD ROCm, right?
Yeah.
So,
So
and
for
Intel keeps renaming whatever they're doing, one API or whatever it's called now, right? So
yeah, I think one API is what they're going with. But it's one high-level API that's a leaky abstraction for a lot of other things underneath, and you still have to kind of poke through it to do any work on different platforms.
and by the way, Jay, so uh it's reasonable. Is it reasonable if, like, let's say I'm AMD, right? So I should invest in ROCm. Why should I invest in Triton?
Yeah, so if you are
Is that a reasonable move on these hardware companies' part?
absolutely, I think it is,
Yeah.
right? So if we do end up in a world of heterogeneity, someone has to build a stack, right? Now, if one of the semi companies builds the stack, everyone's beholden to that semi company and how they influence you, right? If one of
And
the cloud,
there's going to be lack of trust there, right? So that stack might be perceived as running best on their hardware.
yes,
Yeah.
right? It'll always be like if I'm building for my own hardware and it kind of works on yours, it will work on yours, but not as well as your own stack will work on it, right?
Right.
And part of the reason, like, if you look at CUDA's success and what made NVIDIA successful, it was CUDA, PTX, and the GPU architecture together. Had those three things not been done or co-designed together, I don't think they would have been where they are today. Now, ROCm built a pretty decent stack, but they haven't thought about, well, developers care about productivity and they don't want to rewrite their code for every single new hardware. They just want things to run and they want things to get faster for every generation of hardware. So you need to have something like PTX in there that you can use to get things to new hardware and make sure they actually fit together. And so that portability and performance part has to be there. And you have to have a good abstraction for developers to actually use. Right? So if a programming model, execution model, and the hardware are not tightly coupled, you're not going to get performance. Or at least you're going to make it very hard for a developer to actually get performance. Right? And ROCm and the AMD team, as much as I love them and how much respect I have for them, they've had struggles with software side, right? Every semi company's had struggles with software side, right? And NVIDIA's thing is they kind of view themselves more as a software company than a hardware company, and they act like it.
Yeah. They talk like that too.
They
Yeah.
do, and that's part of their core DNA and what makes them so great. And I want to make every semi company like that and make it easier for them to get there, right? But it's a mentality shift. And making a mentality shift like that and accepting that change is the equivalent of having to do a brain transplant most of the time because people don't want to make those changes. So we've basically built an equivalent to that kind of a stack that everybody else can bring their own code generators into and leverage so that the cost of software is amortized across all of those hardware providers. And it's simple for developers to use a single stack because developers.
So right now, if I look at your software stack, uh, what what silicon are you comfortable? Okay, we're there for this hardware.
Yeah, right now we're up and running on CPUs and we
Okay.
started working on GPUs.
Okay.
We started to get early results on GPUs. We're roughly on parity or better than on most CPUs for different kinds of workloads, running straight from PyTorch. And that was like one of the first things we wanted to see is like, can we actually take things from PyTorch and eat them and then get them running on hardware and do it performantly,
So
right?
CPUs meaning Intel, AMD, ARM.
Yeah, right now. Haven't done ARM yet. We're about to get a couple of different pieces of hardware from different vendors to start doing that. Right now, we've got AMD GPUs and NVIDIA GPUs, and we're working on those.
And so what's the challenge, Jay, for building and so actually before you answer that question, so let's say you get there, right? So
Mhm.
you build something. So what do you think the impact will be for a developer or an AI team? What are some of the benefits that they immediately will reap from you building this software stack?
Yeah, so if you're operating on a cluster of like north of 1,000 nodes, for example, right? That's like 8,000 GPUs. You should be able to comfortably get somewhere between a 3 to an 8x improvement on training runs in terms of speed. That's huge, right? The amount of cost savings from that is ridiculous. Like
So this
either,
is pure software. You're not messing around with interconnects or InfiniBand or nothing. Yeah.
and
Or memory.
no, like this is just compilers and runtimes, right? There's a ridiculous amount of things that you can do inside that
The
if you do it.
same cluster that I'm using, you're not gonna touch the hardware.
Yeah. And same thing for inference. There's a whole set of things that we make available through the stack and on top of it, so that your job taking a trained model and putting it out there in the world is much easier, right? And you will get a whole lot more performance out of that hardware because when you're,
Oh, so what you're describing here is deployment, so not training.
yes.
Okay.
So the stack is built for both, right? You have to go both, right? You want to take the trained model, you want to package it, and you want to deploy it. You don't want to have to navigate through a whole separate other set of tools and stacks and think about how things are breaking so you can do that. Right? You don't need an army of people every single time you want to do something.
And honestly, most enterprises are not going to train foundation models from scratch. Maybe they'll customize, fine tune, but most of it is going to be in deployment, right? So
Yeah. Yeah, for a large chunk of people, right? So you will see some things happen. Like I don't think everyone's going to build a large foundation model for themselves, right?
but
Because that
even if they do, it'll be very targeted and specialized, right? So foundation model for some specific area in healthcare or something, right? So
yeah, so I kind of see it as two things, right? So you're going to have model companies and data companies, and it's kind of this how I generally break them out. Model companies are, your OpenAIs, Anthropics, and so on and so forth. And then you have your data companies, and that's companies operating inside of verticals, and they're building slightly medium-sized models. And those could be foundation models that they make available in that industry, or companies building models for themselves for proprietary use cases, right? And then you can kind of like interleave them together in like a agentic way, and then you can benefit from both of them. So there's a lot of things that are going to be happening.
so right now, so you folks are you've built your software and you're testing it out on CPUs. Results look promising on CPUs. What's the timeline to get to the GPUs?
By the end of the year,
Okay. And
yeah.
so end of the year, what are you in comparison to Triton in terms of
So when you're looking at
feature
Triton, you have to look at Triton,
features or capability? Yeah.
I think about 80+%.
Okay. Uh,
Uh, it's always corner cases you have to think about, and those don't rear their ugly heads until you actually get there.
So you said, like you said earlier, right? So PyTorch has a few thousand operators. So you're going to have to support all those operators, right?
Yeah, we stumbled into a couple of really cool things that allow us to move as fast as we are, right? So if we did what Rockham did, try to actually build our own version of CUDA, right? That kind of forces us into thinking of platform-specific kernels. And when you're thinking about platform-specific kernels, you have to think about the different workloads, the different way things will fit together, how to get that on different kinds of hardware, rewriting those for different kinds of hardware so they're performant and developers don't have to think about them. That comfortably requires 1,000 engineers, right, to actually build and maintain and extend and so on and so forth.
Which is what AMD and NVIDIA have.
Yeah. And if you are doing that, you're always going to be 10 years behind NVIDIA,
Yeah.
right? Because they have way more
Yeah.
and
Yeah.
skill at this.
Yeah. Yeah.
So you kind of have to do for all the Trekkies out there, you kind of have to do Kobayashi Maru. You have to change the game. And you have to think about a non-platform specific kernels way. And that's a lot of what we've done. And if you want to solve for heterogeneity, you have to kind of blow out that entire thinking. And you want to be thinking about how you kernel launches at runtime for different kinds of hardware and what are the different elaborations you need and what kind of information you need in order to do that well so that you don't have to do it ahead of time. Right? So there's a lot of cleverness inside of this that allows us to get as far as we have with the number of people that we have.
So do you have an official channel of communications with the CUDA or ROCm teams?
Not with the CUDA team. We are talking with a lot of the other semi companies out there. We are hoping to engage with the NVIDIA team soon. But
And do you have a relationship with the Triton?
we're talking with everybody in the industry right now.
Okay. And what about license? Is it open source?
There will be parts of the stack that are open source, and there's parts that are going to be closed, right? There's some really proprietary things that we're working on that we want to maintain as closed because that is where the most value comes from, and those we don't want to just put out there in the world. But the top part of the stack, we want to make it open so that people can contribute and use it to build an ecosystem around, because there's some things that they need to have control over, but there's other things that they shouldn't have control over. And we want to make sure we get that right as we're releasing things.
So in your case, you're just focused on supporting these PyTorch operators, right? So if there's some other breakthrough, let's say Transformers 2.0, your software should still work. Although right now I don't see a Transformers 2.0. People are talking about Mamba, but I don't know. It
I
seems
think
like
the story is
it,
yet to be written.
yeah. What's your sense?
I think a transformer architecture is insanely powerful. Underestimating it is a mistake, but I also don't think it's the last architecture we will create.
Yeah. It can't be the last word. Come on, man.
No, we'll definitely create more architectures, right?
So here's my fear, Jay. Right. So
Okay.
Transformers came out when Google and the industry was, relatively open. Here's the Transformers. We'll publish the paper, right? So what about in the future? If in the future they go, okay, so we had this breakthrough. Here it is. You can use it on Google Cloud or some other cloud, and
Right.
here's a very kind of high level description of what we did, but we're not gonna share anything. Now, the counter argument to that is all these people go to the same parties and go on vacation together, so maybe there's no secrets anyway. They go to the same conferences. You know what I mean? So
there's a lot of very poorly kept secrets in the industry. That is true. I think there's every single AI group worth its salt is looking at an alternative to transformers right now.
Yeah.
So I wouldn't be surprised if there's new architectures.
Yep.
I wouldn't be surprised if all of them end up converging on a similar kind of architecture, because most of the knowledge is already open, right? It's how you piece them all together and how you scale them up that becomes the secret sauce.
Right.
So how you're doing your pre-training for the case of transformers, that is somewhat unique to different kinds of companies. And if somebody from an existing company goes through that, to kind of bring that with them, of course. Because you can't lobotomize people when they're leaving your company.
But you're building your stack so that if there's a transformer 2.0,
Yeah.
you're still relevant.
I am fully expecting a world where things will change faster than people think, and I want to be prepared for that.
So obviously in this world, right? So there's compute, there's the model, but another thing that people are increasingly competing on is data, right? So what's my training data? Can I license this data? Can I do some sort of clever data quality thing along the way in order to improve my model? So are you cognizant? Are you doing anything specifically around data?
No, not really. For us, I mean, I'm more concerned about the software stack right now
Mhm.
and making sure that we unlock hardware and bring overall costs down, and making developers happier and more productive. I think a lot of the things around data that people are talking about when it comes to like, hey, we're going to run out of data. I think those things are maybe one or two breakthroughs away from being solved. And I don't think they will take that long to do. Right. So from a language perspective, you have about 30 trillion tokens worth of usable data, right? When you actually go towards multimodality, somewhere between 250 to 300 trillion tokens. So that tells you models can get quite a bit bigger, right? And if you start going towards synthetic data and self-play and a whole bunch of other things, it stands to reason you can actually get another 10x, right? And that'll inform again how big models can get. But there's other algorithmic breakthroughs that we can have, and then eventually we want to try and get towards sample efficiency. And hopefully we get to a point where models can learn in situ, right? Once they're being deployed, because that will be a whole other unlock, and that'll switch things more towards deferring computation from training time over to inference time, and then reasoning there and learning while it's doing that, and that will reduce a lot of things, right? So right now, if you think about the state of models today, and if you fix that, right, models aren't going to get bigger, they're not going to get a whole lot better. But if you get mass adoption, right, if there's about a billion people or 100 million people trying to use this on a daily basis,
No,
you think,
this is one of my things, right? So sure, the foundation model companies are having kind of economic challenges right now around the cost of training, the cost of deploying, and their personnel costs and all of that. But set that aside, if for some reason they can't train another model, I mean, the models we have now, we can mine them for another few years in the enterprise, right? For applications, right? So
we haven't even scratched the full surface of what we can do with the models we have today.
yeah, exactly. Well,
We,
obviously, the operational costs for deploying these models of scale will still be there, but at least you won't have to, if you don't have to train new models constantly, then you save costs, right? So
yeah, I mean,
yeah,
if it take ResNet, for example, right?
yeah.
ResNet was a pretty big model back in its day, and it was one of the leaderboards. But every single year, the cost of it has gone down by about an order of magnitude.
Yeah.
Right? So in 9 years, you go 9 orders of magnitude cheaper. That's pretty good, right? So if you kind of stay where you're at, we'll find ways to make things cheaper. Like
Mhm.
human ingenuity is a real thing, right? It's not going away, and we like solving hard problems as engineers. So we will figure out how to make things cheaper and scalable.
So let me do a rapid fire round. I'll throw out some kind of hardware trend or hypothesis, and then you react, and then you can also tell me if it ties into what you folks are doing at Lemurian, right? So
Yep.
first one, memory bandwidth bottleneck, right? So memory bandwidth often limits AI workload performance more than raw compute.
Yep.
Um,
Yeah, that's a real thing. Right. So there's two kinds of operators that we generally have to deal with, right? There's compute bound and there's memory bound. And you've kind of got an interleaving of both of those, especially in the AI workloads. It was true in the graphics days, it's true in the HPC days, it's true now, right? That isn't going away. Like transistors have gotten better, capacitors aren't getting better, they haven't for a while. So you kind of want to focus a whole lot more on bandwidth and making sure that and this is why number formats really matter, right? You want to get good at compressing information and shipping them so you're storing more information in fewer bits, and that saves on bandwidth. And if you can flood the system with more work, then really good schedulers matter a lot. And then how you order your work and group them together allows you to essentially try and saturate as much compute as you can, right? Because
does your innovation around parallel adaptive logarithm, does that play into this? Yeah.
it does.
So can you explain that to our listeners?
Yeah, absolutely. So number systems normally, like, you have integers, right? Integers, or as they are, right, vanilla things. But now you have floating point numbers, right? Floating point is three things. So you have a sign, you have an exponent, you have a mantissa. An exponent is all the large numbers, and mantissa is all the fractional things in between. But it is much cheaper to have the exponents because the exponents are logarithmic, right? And logarithmics are very dense information, and they can store they can grow in size a whole lot quicker. So what we kind of realized was, well, we can essentially mix or interleave two exponents together and use that to recreate the kind of distribution you would get from floating point, especially for smaller values. Now, that's very high level. Of course, don't want to get too into the weeds. But what we found is this thing scales extraordinarily well and has really nice numerical properties and nice closures for multiplication and addition. Now, we can, in the format that we have, cover FP16 instead of 8 bits, right? So if your models are really stable in FP16 and you store everything in a Pal 8 format and you ship everything in a Pal 8 format, you've just saved 2x on bandwidth.
That's awesome.
Yeah, so like that's something that's coming purely from software. Like, you pay a little bit of price for decoding into floating point at the end in your unit register, but that overhead is negligible.
All right, so item number 2, networking, right? So networking challenges. Networking obviously is crucial for large-scale training across data centers. And high-speed networking is something that's at a premium.
Yeah.
Is this still true? And if it is, do you guys help in this area?
I think good software will always help in alleviating different kinds of challenges in different places, right? So you want to exploit locality wherever possible, and that's one of the things good optimizations do, right? You want to minimize communication as much as you can, because the moment you go off chip, you pay a penalty, right? So think about it. For every single memory access on a chip from an SRAM, you want to have at least 10 to 100 cycles of compute. If you go further, you want to have like another order of magnitude. If you go further, you got another order of magnitude.
This is the whole Cerebrus thing. Let's have a pizza. Huh?
Yeah. I keep thinking about that chip and the programming challenges that may come from it. Now, I haven't dealt with that chip, so I can't say.
Yeah.
But from a theoretical point of view, it seems somewhat challenging.
Yeah, it's actually they don't sell a chip; they sell a supercomputer, basically.
Yeah.
So yeah.
Yeah, they have to, because
Yeah.
there's nothing that it plugs into.
Yeah, and also, I mean, just I mean, they have their own cooling system.
Yeah,
and things like that. Which, by the way, which brings me to another trend, which is something you alluded to already: specialized supercomputers, right? So,
yeah.
So will this lead to I guess in your mind, what you're building will mean that these specialized computers will still be inherently something approachable to regular developers, as opposed to needing some sort of specialized software or specialized hardware, right?
Yeah, so I don't want developers to have to constantly go and relearn how to write software for every single new kind of hardware. I think that's a waste of their time and talents, right? And it's not what they should be thinking about. I want to make different kinds of hardware easier, right? So Cerebrus chip, if it's that big and has that much bandwidth, it could probably accelerate training by quite a bit, right? Now, there's other chips that they're really good for inference, right? Make it easier to use them, right? You want to make new hardware easier to use. And if we get into a world of chiplets, for example, which it seems like we're on trajectory for, that's different IP from different vendors stitched together, sitting in a package, and each of them has their own cycles. So you could, in theory, swap them out. Now, if that happens, you have to go and completely refactor your code every single time. Why? There should be a better way to do that. So let's have the better way. Right? If this is the world we're all expecting and we are going into, let's make sure we do it right. It shouldn't be the case like in parallel computing or in the early days, in the early 2000s, that we had parallel computers, but it took us a decade to build the software to start using those things. Right? Let's get it right at the very beginning so that software is there to greet that world.
And by the way, Jay, so to the extent that AI will be one of these really disruptive things for enterprises, right? So if you think of cloud computing, right? So even enterprises, even when they go to the cloud, they still have maintain some sort of on-prem uh, applications, right? So they're usually hybrid. So in the AI world, you can imagine a world where enterprises also are sort of hybrid, right? So where they use supercomputers in the cloud, but maybe they will have to run some supercomputers on their own. And
Yeah.
in which case, why not make those supercomputers as approachable as possible, right?
Yeah. So I think it's totally reasonable for a lot of companies, and a lot of companies are thinking about this right now, building supercomputers for themselves for training, but then go inference in a cloud environment, right? Because for obvious reasons, right? Total cost of ownership being one, and then cost of operations and a whole bunch of other things.
Or
So
there might be actually legal or regulatory reasons where you have to do a lot of things off
possibly,
cloud, right? So yeah,
so that it's definitely true as well, right? So
yeah,
if you're
yeah.
working with a tool at an acronym agency or in a certain industry, you kind of have to be disconnected from the internet for the most part, or in an air-gapped place. So that is a definite reason and something that would happen. So if you get into the world of sovereign AIs, for example, they don't want their data leaking out completely. They want to have ownership of it. It's just the whole point of having a sovereign AI, right? Is make your data accessible for yourselves and keeping it there. Um, so yeah, all those things are happening. They're real. There are conversations happening all across the world, in every single boardroom, in every single company, in every single place. Yeah.
All right. So one last thing, which is on device, edge and on device inference, and maybe this notion of hybrid intelligence, right? So where maybe some of the compute gets done on the edge, but some of the compute gets done on the cloud. Uh, that definitely seems like it's going to be a thing moving
Mhm.
forward. And does your software stack help there?
Yeah, that's a good question. I think Edge is a real thing, and it's going to be a thing, or even a
Mhm.
bigger thing. I think a lot of people rushed into it too early because things always trying to trickle down from the data center down to the edge. So we kind of need this continuum to happen. I came from the world of robotics for the most part, right? So I've been dealing with the edge for a very long time, and I've been waiting for its moment. Um, and yes, the stack is designed to go from edge to cloud. Right? I do want to help people connect those two worlds.
By the way, Jay, one of the it's obviously we're all focused on LLMs and language, but people forget that the computer vision and speech people they've been kind of innovating on the edge for years, right?
Yes.
I mean, sometimes even uh, on cameras and sensors that are not even connected to the internet there, right?
Yeah.
So you can imagine your home appliance or your refrigerator. Maybe you can just go up to your refrigerator and ask it to, do RAG using a speech interface, right? So ask it about, hey, I'm trying to do this, right? So it may not need to be connected on the internet, right? So
Yeah. I
yeah,
think local intelligences in different areas will have to be a thing. Right? And it's different for every single application, right?
right.
So how you do a self-driving car is different from how you do a household robot versus an IoT device versus something happening in the industrial IoT space. Or if you're in the healthcare space, you have a different set of things or different constraints to think about. So yeah,
But I guess my point is that, this new generation of younger developers who are coming into this space in the world of LLMs, they may have missed kind of the what happened in speech and computer vision. All
yes,
of the clever hacks that all those people did over the years, right? So
yeah. I think there's a lot of knowledge that is getting lost in some areas because it is absolutely daunting to try and keep pace with things that are happening, right? So you kind of have to draw the line somewhere. Like you can't boil the ocean and read every single piece of paper that's ever been written for the past 30 years. Now, unless you were there, it's easier, right? But yeah, there's days that I struggle, like having worked on a lot of these things, and I'm like, oh right, that was a thing. Like we should probably think about bringing that back. But if it's not in your immediate memory, it's not something you're thinking about actively. And today, the name of the game really is scale. So if you're not scaling or thinking about how do you actually get models to scale, you're not totally relevant from in the eyes of the rest of the world.
So your software stack, I would imagine will be called Lemurian software, or do you guys have a name?
Yeah, it's called Title right now.
Title. Okay. So then, so title will be a software stack from Lemurian Labs. There will be a portion of it that's open source. I guess GitHub open source. I don't know if you guys have thought about what license you're going to use. Um, so how do you get people to use something? I guess you have to make sure that it actually works as advertised. There's good documentation. Um, but basically, yeah, you've got to make sure that people are productive from the get-go, that it works as advertised. Because otherwise
Absolutely.
they may not give you a second chance.
That is very much true, and it's a thing that we think about constantly, right? So if you ever at Lemurian, like we have these things like we like doing pre-mortems a lot, and it's basically let's try and kill the company before we actually end up something else happens, and that way we can be better about reasoning through it and solve for that. And one of the things that we're constantly thinking about is developers, because they're our customer and that's who we care the most about. So what do we need to solve for to make them happy and solve for adaptability, right? Because if we don't do that, well, we don't have a business. It doesn't matter what we build or how cool it is. So part of our go-to-market is partner with the semi companies and the CSPs and so on, and they kind of become our partners in a way to serve all those customers. So
Right.
once things are tested out in these environments for them, they know that things will scale, know that things will work. Those interfaces are all defined. And because other companies are part of this ecosystem, they know it's going to be well supported, right? So that reduces a lot of the risk for them to be able to use it. And then we'll do a lot of the benchmarking for different kind of operators internally and different kinds of workloads and show them like, hey, this is how things run normally. This is what it looks like to do this thing. If you want to do training, this is how it runs. This is what the scripts are like. This, if you want to do inference, this is how you would do it. This is the kind of performance you can expect. This is the kind of things that you need to be responsible for as a developer and what we will leave to you to do. And these are things that we will take care of and do really well.
So who are the guys that came out of Google who are doing kind of the compiler? You remember? Uh,
Um, There was not AI at some point. There was modular.
Modular, yeah, yeah, yeah. So, is there, do you have any kind of overlap with modular?
I would imagine so.
Yeah.
Probably a little bit. I don't know
Yeah,
their
but
exact
they're
roadmap
almost
or
like taking what they're doing is kind of taking Python and kind of making it run faster. They have
well, it's a new language.
right, right. Yeah, yeah, it's a new language, but basically Mojo, right?
Yes,
Yeah, yeah,
it's a
yeah.
new language.
Yeah, yeah, but basically they're trying to make it so that it's seamless for someone in Python to to move over, right? But I don't
Yeah,
know. I mean, that seems like an uphill battle to me. Um,
languages are hard. You really
yeah.
don't want to go there unless you have to. Now, Chris is
Oh
very
yeah, yeah.
experienced.
I mean, obviously, as
Yeah,
far as programming, you're in the Mount Rushmore there in terms of
yeah.
yeah, yeah,
Uh, if it came to a battle of programming languages, I don't think I'd want to go up against Chris.
yeah, yeah,
And
yeah.
he is. I have.
It's just that the ecosystem around Python is just
It is tremendous. It is.
yeah.
It is currently the language of AI developers, right? There's no denying it. The massive ecosystem, developers are comfortable there. Like it is hard enough to do all the things in ML, but then also to have to be a really good programmer and know low-level languages and how to understand hardware and get performance out of it. It's really hard, right? So you need a high-level interface to be allow you to be productive, and that's part of the whole point, right? So C, was successful because the programming model for C, the virtualized memory model, and so on and so forth, and was very tied to CPUs, right? And they all kind of like went off of each other. Same thing with CUDA. CUDA, PTX, the execution model, the programming model, and the hardware were very tightly defined together. So you kind of need that to happen, right? And that's becomes very complicated to do well when you think about heterogeneity and scale, but you kind of have to solve those problems. Right? There's no other way to do it. There's no bypass, but you can't do it when you're low level. That makes it harder. So you kind of have to have the right degree of abstractness to be able to mask some of the hardware, but also make it easy to get performance out. Right? So you have to make good choices there. And Python is very high level, but it could work out.
Yeah, and obviously Python has many weaknesses as well. I mean, one being the Python software supply chain is increasingly complex, right? So
It
you
is.
install a package and then it's installing like 50 packages as it's installing the package and you don't even know what it's doing, right? So
Yeah, I mean,
okay, so in closing, how do people get involved? Is there a website? Is there, are you hiring? So,
we are definitely hiring, and we're going to be hiring a lot of people very, very soon. Um, we will be releasing a lot of things on our website and ways of engaging with us, and we're starting as we're building the community out. Um, you'll be seeing all of that happen over the next 6 months. So for all people out there that do want to learn more, that's where you do it. Go to our website. There will be places to go. We will have a whole lot of things on GitHub that we're releasing as well, and you can all contribute to it. You can add to it. We'll have a place where you can actually chat with us and get feedback on things. All of those things are coming down the pike.
and with that, thank you, Jay.
Thank you.